I would like to begin by thanking the organizers for putting this conference together. It looks like it's going to be a really interesting few days. And also for inviting me to start off this session. So the subject I want to talk about today is one that increasingly I feel is central to planetary atmospheric evolution and also to the way we should be thinking about habitability and biosignatures. And I've titled it Abiotic Oxidation, but really more generally what I want to talk about here is planetary redox evolution. So I'm going to begin with some real generalities, and I want to do this in the spirit of people coming from lots of different backgrounds here. Once I've done that, I want to discuss some actual data first off. So we're going to talk about trends in the solar system based on what we know already, starting with Venus and then moving outwards, all the way to some outer solar system objects, so Titan and Ganymede. And I will then discuss how we should go about modeling redox evolution, and I'm going to do this in a context of really focusing on the early stage of evolution, and in particular the period where planets have magma oceans, which in many cases is likely to dominate the subsequent redox history. And then kind of mixed in with this discussion of the modeling, I want to talk about the importance for terrestrial type exoplanets. And so this includes false positives for life, most notably abiotic O2, but also their habitability and potentially their prebiotic chemistry. And I'll finish by discussing some future goals, both observational and theoretical. Okay, so if you have a physics background, you may be more comfortable dealing with equations like this, and possibly electron orbitals like this, than thinking about other concepts in chemistry. So just for starters, to think about oxidation reduction, the key thing really is to remember this phrase. Oxidation is loss of electrons, reduction is gain. And so a classic example of an oxidation reaction is the reaction of oxygen with iron, metallic iron, giving up electrons to form more oxidized iron. So one example being the hematite, which is seen in red beds on Earth. An example of an oxidized planetary surface is Mars. Its classic reddish appearance is also due to oxidized iron. An example of a reduced atmosphere and surface is Titan. In this case, it has little to do with iron, but it's the presence of reducing gases like hydrogen and methane there. And so when we're thinking about redox, the first thing you have to think about is elemental electronegativity. So every element can be assigned a number which describes how what potential it has to do oxidation or reduction. And you can see in the periodic table, there's this clustering around oxygen and the halogens of high elemental electronegativity. But of course, if you're thinking about planetary science, and especially about broad brush processes, we don't care about all these elements. So you also have to think about elemental abundances and the galactic abundances are a strong function of atomic number and also highly nonlinear as a result of stellar nucleosynthesis. So when you take these two pieces of information, you can produce a plot that I think is quite informative about what we should expect for general trends. So on the x-axis here, we have electronegativity with more potentially oxidizing species in this direction. On the y-axis, there's atomic mass. And I've plotted the 8 most abundant elements based on solar system abundances. 2 of these, magnesium and silicon, tend to bond early on with oxygen, usually in the protoplanetary disk phase, and subsequently mainly remain in the planet's mantle. And 3 of them are important, carbon, nitrogen, and sulfur, and relevant to climate, but generally speaking less abundant than O and H. So when we're thinking about redox in the broadest possible terms, it's these big 3, hydrogen, oxygen, and iron, that tend to dominate. And iron is higher mass, tends to be segregated towards the core. On terrestrial mass planets, hydrogen tends to escape to space. And as a result of this, there is always a tendency for oxidation on terrestrial type planets. So I think that I like to emphasize this plot because I think sometimes when we're thinking about abiotic oxygen, it's seen as this novel and unusual phenomenon that is put forward only theoretically. But really, oxidation is a generic outcome, and it's really about the degree to which it occurs to determine whether or not we should see abiotic oxygen appearing in planetary atmospheres. Okay, so that's like the sort of broad brush cartoon picture. Let's talk about some data now. So redox trends in the solar system. We're going to start with Venus. Venus, as is now pretty commonly accepted, most likely went through an early runaway greenhouse event. Today, it's got a 90-odd bar CO2 atmosphere and is desiccated, but in its early evolution, if it had liquid or water oceans, once the solar flux gets to a certain point, there would be an instability that occurs where you have all of the oceans evaporating and becoming H2O in the atmosphere as steam. And critically, the cold trap in the tropopause, which keeps Earth from losing water today, would be removed. So in this situation, when you have high energy photons from the sun, you can photonize H2O, you produce OH and H, and then the H and some of the O will be lost to space. So this is a pretty compelling picture for what happened to Venus, but there's a big question hanging over it, which is where did all the oxygen go? Because you don't lose nearly as much oxygen as hydrogen, and most models indicate, starting from studies that have been performed in the 1980s, that you should have up to oceans worth of oxygen that are left. So a potential solution to this is that Venus actually didn't have liquid water in the beginning. It was instead losing its water during a stage where the surface was so hot that it was molten. And so under this circumstance, what happens is that oxygen that gets liberated in the atmosphere is going to go down and react with iron in the mantle. And you end up with a net oxidation of the mantle, but not oxygen appearing in the planet's atmosphere. And so there are models which fit noble gas isotopic ratios that are in line with this. And it also, I think, fits with the limited data that we have on the oxidation state of Venus's surface. So this comes from just a few data points from the 1980s Russian landers. We definitely need more data, but the indication is that the Venus surface is near the magnetite-hematite boundary, which is more oxidizing than that of Earth's mantle in general. So at this point, I should probably give a quick note on mantle redox chemistry, because this is important to the discussion as well. The concept of oxygen fugacity is central to thinking about mantle redox chemistry, and it can sometimes seem a little esoteric, but basically oxygen fugacity is just oxygen partial pressure under ideal gas conditions, and it's best thought of as a yardstick that the mantle geochemists use to assess oxidation state. You never actually measure it in practice when you're looking at mineral systems. You instead measure various mineral buffers. And so as a function of FO2, one of the most reducing is iron wustite. A more intermediate mineral buffer is phyolite magnetite quartz, FMQ. And then the most oxidizing one is magnetite hematite. And so it looks like Venus's surface and possibly also its mantle are somewhere here on this redox scale. Okay, so now let's talk about Earth. Earth has an oxygen atmosphere, the proximal cause of which is life. And we're kind of used to thinking of it as the most oxidized planet in the solar system for that reason. But actually, the initial redox state is critical, set by abiotic processes, and significantly more reducing than the state of the atmosphere itself. And it's extremely well supported by the observational evidence that Earth's early atmosphere was oxygen-free, and it possibly may have been strongly reducing, particularly early on. It's possible that in the Archean, there may have been extensive oxidation by biogenic methane emissions. So what happens here is that even if the planet still has a strong cold trap, but methane is more volatile, so it can go up into the high atmosphere. And that allows you a way to transport hydrogen high up that gives a net loss of hydrogen, a source of oxidation to the planet. Something known as redox disproportionation may also have been an important process in mantle oxidation in the Hadean. This is something which occurs where moderately oxidized iron disproportionates into highly oxidized iron that stays into the mantle, and then metallic iron, which it's generally assumed eventually sinks into the core. And so observations of Earth's mantle suggest that it's in the upper mantle near this phayolite magnetite quartz buffer. And there's been several arguments that this redox disproportionation may have been a significant factor in determining the redox state for Earth. So Earth and redox is a complicated subject, and you could spend an entire talk on it. I'm not going to do that here, but I do want to highlight one other aspect of all this, which I think ties in with other elements than oxygen or iron or hydrogen in an interesting way, and that's nitrogen. Nitrogen is sometimes thought of as a bit of a boring gas because it just sits in the atmosphere or was once thought of as a boring gas that just sits in the atmosphere, but it's recently become apparent that it has both greenhouse effects and long-term trends in its evolution. So it can cause warming through pressure broadening. Also, if you have reducing conditions, it can cause strong warming through this collision-induced absorption effect. And in addition, if on Earth you have low nitrogen, then it's also a route to potentially high water loss and planetary oxidation, even if you're not anywhere close to a runaway greenhouse state. And the reason for this is that when the partial pressure of nitrogen becomes low, the tropopause moves upwards, and eventually you get to a point where water vapor can get into the high atmosphere. So again, those H2O molecules are exposed to UV photons, which can disassociate them and allow enhanced hydrogen to escape to space. So we hypothesized that this would be an important process for exoplanets a few years ago. And most recently, there's been an interesting paper by Kleinbol et al. Where they looked at this using a coupled climate chemistry model. And they showed that for partial pressures of nitrogen as high as 0.1 bar, it can be a really significant route to getting abiotic oxygen still. And I think it's a very interesting general question that given that there's observations of varying nitrogen levels throughout Earth's history, that if biology did play an important role in mediating nitrogen, then there may have been potential links between redox and the biospheres through this route as well. Okay, so rushing through the solar system now outwards towards Mars. Mars is another interesting case for different reasons. Mars is rusted red, so it clearly has a hyperoxidized surface. There's a lot of oxidized iron and likely compounds like hydrogen peroxide and things near the surface. But in many cases, it looks like this oxidation is literally skin deep. So if you look, for example, at some of the drill cores done by the MSL rovers, and of course there's detailed geochemical analysis behind this, but the visual appearance of this is very striking. You have highly oxidized iron on the surface, and then you don't need to drill very far before you start to see reducing conditions reducing mineralogy pretty quickly. And further evidence comes from the SNC meteorites, the Martian meteorites, which suggests that Mars's mantle is actually more reducing than that of Earth's. This is a plot of data here where it shows that it's more towards the iron wustite buffer than the QFM buffer. And physically speaking, it's clear that because of Mars's greater orbital distance, any magma ocean water loss phase would have been extremely short. So that supports the idea that that route to oxidation wouldn't have been significant. And finally, reducing gases may have potentially been very important for Mars's early climate. And so a number of mechanisms have been put forward for either long-term or episodic warming of the Martian climate through CO2 in combination with hydrogen and methane in a similar kind of fashion to the way that nitrogen and hydrogen are known to cause warming through CIA. So going back to this FO2 yardstick for oxidation picture, we can tentatively say that if we're talking instead of about the atmospheres, the bulk, the oxidation of the planet's upper mantles and atmosphere together, there seems to be some trend with orbital distance. So with Mars being more reducing and Venus being more oxidizing and Earth somewhat in the middle. I've added a bunch of question marks here because I want to emphasize that I'm basing this, particularly in the case of Venus, on limited data, and I think it emphasizes the point that we need increased data from the solar system. But based on what we have, it looks like there's this trend with orbital distance. So moving outwards finally to the outer reaches of the solar system, I want to finish up by talking about Titan and Ganymede. So Titan, everyone's favorite moon with an atmosphere, is in orbit around Saturn and has a 1.5 bar nitrogen atmosphere, or otherwise has highly reducing conditions. So abundant methane, significant amounts of hydrocarbons and organic hazes, and methane plausibly emitted from clathrate destabilization in the subsurface, which this idea was actually part of our inspiration for thinking about clathration on Mars and reducing episodic warming through that mechanism. So again, Titan sort of fits with this trend of, as you move outwards in the solar system, it looks like you have more reducing conditions, but then just to keep life interesting, we have the example of Ganymede, which is in some ways sort of like Titan's twin. Its mass is similar, but its atmosphere is entirely different. It's extremely thin, and it's dominated, we think, by bimolecular oxygen. It appears to be the only example in the solar system, well, actually Ganymede and perhaps some of the other moons like Europa, of atmosphere which is abiotically created but dominated by oxygen. And the origin, it's thought, is again H2O dissociation. So you have the hydrogen being lost to space and then oxygen building up afterwards. Except in the case of Ganymede, because it's so small and it's in a high radiation environment, the oxygen that gets liberated itself escapes fairly rapidly after that point as well. Okay, so I want to go on to talk about exoplanets in a moment, but before I do that, what lessons have we learned by thinking about the solar system? Well, first of all, I think it's critical that the distinction between the planet's bulk redox state versus its atmospheric redox state is extremely important. Primarily because you can build up O2 in the atmosphere abiotically, but it's also extremely easy to either lose it to space or to the planet's interior. And in general, I think a case can be made that mantle oxidation appears to decrease, or at least upper mantle oxidation decreases with orbital distance, but we need more solar system data, and I think a surface Venus mission would be pretty high up in those list of targets. So, okay, I think what's doubly exciting about the current era is that we have this potential now, which we never had previously, to expand our understanding of these trends by looking at a diverse array of exoplanet targets. Furthermore, of course, we have this opportunity that we may be able to use our understanding of redox variations to start to think about implications for life and for biospheres, including the search for potential false biosignatures. So let's talk about redox now outside the solar system. First point to make is that although we're interested in all star types, and eventually, when we're thinking about the next decade of observations in particular, the game is really going to be observation for terrestrial mass planets around M dwarfs, and for various observational reasons, which I'm not going to get into here. Red dwarfs are distinct from G stars in a number of ways which are important. Firstly, their lower luminosity means that if you want to have a planet receiving Earth-like fluxes, it needs to be much closer in, under which circumstances it's likely to be tidally resonant or locked. From an atmospheric evolution perspective, even more important is the fact that these stars are extremely active emitters of XUV radiation and have high stellar activity, and so atmospheric loss should be very enhanced in planets around in these systems. And that's true for H2O and for hydrogen, but also for heavier gases like nitrogen and CO2. And then the final point is that, as pointed out in this paper by Luger and Barnes a couple of years ago, there's a extended pre-main sequence phase that these stars undergo, which has probably extremely important consequences for the planet's evolution. So, in particular, planets that are later receive Earth-like fluxes will have an early extended steam atmosphere phase where they have magma oceans, and they should be losing significant amounts of hydrogen to space. And so I think a very important question is whether or not these planets are going to be hyperoxidized from water loss with abiotic O2 atmospheres, or whether we expect that, that something else might happen. So so in the remaining time, I want to talk about a specific modeling exercise that we did to address this question. And this is building on work by numerous other authors. But the essential idea here is that we're coupling together different components of the planet system in order to get an integrated view, not just of the atmospheric evolution, but of the interior evolution simultaneously. So we have a stellar flux and atmospheric escape model. We have a line-by-line climate model. There's an atmospheric chemistry component and a model for the magma ocean and mantle outgassing. And for this component in particular, you'll hear more later in the week when Laura Schaefer presents her work. So the setup for this model is based on this thinking that I described previously, where we want to simplify things as much as possible. So we focus just on hydrogen, oxygen, and iron. Given that, we have these redox active species in the volatile layer and the mantle region. And you can write things down in terms of a box model where you're looking at the oxidizing power in each region. And the real challenge, of course, is understanding how these K exchange terms change with time and how this escape term changes as well. You may note that I have an escape term with an arrow pointing downwards. This is because this N here is the oxidizing power of the system. So net escape of hydrogen to space means an increase in the oxidizing power of the volatile layer. So the initial conditions in the model are that we start in a magma ocean state, which is reasonable given the heat flux that we would expect from accretion, and particularly for M stars as well, the high pre-main sequence stellar luminosity. We're right now assuming rapid early core formation, so that allows us to eliminate these two exchange terms here and just focus on the exchange between the mantle and the atmosphere. And we vary the initial mantle FeO in the range from 0 to 20%. This is a wide range, so we can understand sensitivity to this parameter. Average values in the solar system are around 8% or so. We vary H2O, the initial H2O abundance, in the range 0 to 1%. The thinking here is that if you go much beyond 1%, then you're getting into a situation where you would be able to tell that the planet was volatile rich from its mass-radius relationship. And at least in the plots I'll be showing you here today, we assume no initial H2 envelope. And so, as I've been hinting at, a key question here that we want to answer is whether runaway greenhouse planets should build up O2 atmospheres or mainly lose the oxygen to mantle iron instead. So I'm not going to talk about all the model components in detail, but the magma ocean model is an important one. For this, we have a model of H2O and CO2 equilibration between the ocean and the atmosphere. H2O tends to be much more soluble in melt than CO2. We have a model for the oxygen partitioning between the atmosphere and the iron minerals in the magma. And the magma melt fraction varies as a function of surface temperature because it's generally thought that magma oceans solidify from the base upwards. So you have a solid lower region, a mush region in the middle, and then an entirely liquid region at the top, depending on surface temperature. And we have a model that treats both loss of hydrogen and oxygen to space, and a line-by-line rate of transfer model for the steam atmosphere. If you're interested in more details of the line-by-line model, I encourage you to tune in to Feng Ding's talk on Thursday, where he'll be talking about applications of this to 3D GCM modeling. How am I doing for time? Okay, so we have an upper atmospheric chemistry model, which I think studies some pretty interesting issues, and I would love to speak about in more detail, but in the interest of time, I'm going to skip forward from this slide. The bottom line is that we found that oxygen building up in the planet's atmosphere does not block off hydrogen escape entirely. It limits it more in a sort of linear fashion. But I want to skip to the results to show the main outcome initially from the atmosphere only case. So now this is first where we're just running the model and not allowing interaction with the mantle. And I want you to focus on the darkest colors here, because the paler colors are extreme upper and lower limits. The dark colors here essentially show that although water loss is a function of the planet's location, be it in the solar system or for various exoplanets, basically in every case there's more reducing power initially in the mantle than there is oxidizing power through water loss. And so this highlights just how important it is to take into account the atmosphere-interior interaction. This now is a result where the models of the magma ocean and the atmosphere are coupled together. And so you can see that there's this strong dependence of the final oxygen that builds up in the atmosphere after the magma ocean phase on both the amount of iron that you initially have in the mantle and the amount of water. I think the dependence in this direction is fairly straightforward. If you have more reduced iron in the mantle, then you can absorb more O2 that's been liberated from the water. The dependence in this direction is due to the fact that if you have more H2O in the system, you have a bigger greenhouse effect, so you have melting going to greater depths in the magma, and hence also a higher reservoir that can be of iron that can interact with the oxygen. And so the net result of this is that for planets with iron-rich interiors and more than a few fractions of percent of H2O, they can significantly lose a lot of water, but not end up building up atmospheric oxygen through this pre-main sequence magma ocean phase. The dependence on orbital distance is extremely important. So for close-in planets like Gliese 1132b, we find that oxygen buildup is significant under most parameters. For more distant planets, the XUV that the planet receives is lower overall, and the magma ocean phase is shorter, and so the potential for buildup in this phase is less. This is broadly speaking in keeping with the trends I think that we see in the solar system as well. And so there's one caveat which I have to add to this, is that I've focused in this presentation on the magma ocean phase, but I've said less about the subsequent phase of the planet's evolution. I think particularly for M-stars, this is still an unresolved problem because, as I mentioned, they can lose even heavy gases like nitrogen to space in significant amounts. And so under these circumstances, once you have a solid mantle, the dependence of the exchange between the mantle and the atmosphere is strongly dependent on what tectonic regime you're in. And so there are still a number of circumstances under which you expect abiotic O2 atmospheres through nitrogen loss and loss of the cold trap and subsequent oxidation. So my best answer to this at this point is that we have to have ancillary observations such as of O2-O2 dimers and CIA and N2-N2 CIA in order to constrain those kind of false positive scenarios from those in which life has created oxygen. But so the general predictions for that come out of this model for a range of the most recently discovered transiting low-mass exoplanets are kind of summarized here. And I think the two most important points are, first, that for the hot planets, which are extremely unlikely to have life, we have an independent way of testing this modeling through observations. For the colder planets, the detection of O2, I think, would be a strong suggestion that life was present on these worlds, because we don't expect through these mechanisms that O2 buildup is going to be significant. And the final point I want to end on is that as well as thinking about this in terms of false positives, we should also be thinking about it in terms of habitability, because we usually focus on liquid water, but the redox state of the planet's atmosphere and surface is absolutely critical to the type of chemistry that you get occurring on it. Most solutions for periodic chemistry on Earth involve combinations of strongly reducing and more weakly reducing or oxidizing chemistries. If your planet over-oxidizes or remains over-reduced, then I think this closes off most of the routes that we know about for prebiotic chemistry. So that's an important point to consider. So I'd like to leave a little bit of time for questions. I think the conclusions are, I will just leave up and take any questions now. Thank you.
All right, so we have time for at least a quick question as we switch over. I guess I could just sling this around.
Yeah, you mentioned M-type stars, but I was hoping your modeling study are not limited to M-type stars, right? Because they do have a terrestrial planet and discovered and observing orbiting the G-type and K-type stars.
Yeah, absolutely, that's correct. And I mean, the best data we have right now is, of course, for G-class stars because we have the solar system, and in the modeling, I wasn't showing the plots, but in the modeling study we performed, we've also been looking at the effects around G stars. I think this pre-main sequence phase for M stars is a really strong distinction, which enhances the possibility that those planets will oxidize significantly. And the fact that the observations are going to be much more readily available for M stars within the next decade is a strong motivator for focusing on them initially. But yeah, I absolutely agree that we should be thinking about G stars as well.